So let's start. Good evening, everyone, and welcome to the latest edition of the IRIS 2.0 webinar series. In this session today, we are shining a spotlight on the Center of Excellence in Geophysical Flows. The center takes a comprehensive approach combining novel field measurements, lab experiments, and large-scale computer modeling to better understand and predict climate impacts, particularly in the North Indian Ocean and its under-observed coastal areas. Now I'm delighted to introduce Professor Manigandan Mathur, the principal investigator of the center, alongside our esteemed panel members and the Geophysical Flows Lab team. Professor Mathur, a leading expert in fluid mechanics, has been a faculty member at IIT Madras since 2012. His research spans aerodynamics and geophysical flows, focusing on internal gravity waves, vortex instabilities, and processes influencing transport and mixing in the ocean. We are also honored to have Professor Debashish Sengupta, a scientific consultant and advisor to the GSL COE, and a Simons Visiting Professor at the International Center for Theoretical Sciences in Bangalore. With over 3 decades of research experience in physical oceanography and air sea interactions in the Indian Ocean, he brings a wealth of knowledge to our discussion today. So without further ado, I invite Professor Sengupta to introduce the other panel members and kick off today's session. Thank you.
Good evening and welcome. It is a privilege to introduce today's moderator, Professor Eric Dazzaro, and our panelists, Professor Emily Schroyer and Professor Amit Tandon. They are known for leading major advances in field measurements and understanding of ocean currents, eddies, and centimeter-scale ocean turbulence from the Arctic Ocean to the Bay of Bengal. In recent years, they have studied monsoon winds, clouds, and storms, and the intricate physics of heat and fresh water in a stratified turbulent sea, and the implications for chemistry and biology of the Indian Ocean. I'm happy to say that our panelists collaborate with the Center for Excellence in Geophysical Flows on science, technology, and student mentoring. Professor Eric Dazzaro is Senior Principal Oceanographer and Professor of Oceanography at the Applied Physics Laboratory and Department of Oceanography, University of Washington, Seattle. He is a recipient of the Swerdrup Gold Medal, a Fellow of the American Geophysical Union and American Meteorological Society, and an elected member of the US National Academy of Sciences. Known for development and innovative use of autonomous instruments, his research spans diverse and extreme environments from upper ocean turbulence under tropical cyclones to coastal ocean fronts and Arctic fjords. Emily Schroyer is Physical Oceanography Program Officer at the US Office of Naval Research. Before taking up her current position, Emily was professor in the College of Earth, Ocean, and Atmospheric Sciences at Oregon State University, Corvallis. Professor Schroyer is known for her research on small-scale ocean dynamics, such as turbulent mixing, internal gravity waves, and the interaction of ocean and atmosphere. Amit Tandon is Professor of Oceanography and Mechanical Engineering at the University of Massachusetts, Dartmouth. Professor Tandon uses his knowledge of fluid mechanics and physical oceanography to address important problems involving upper ocean dynamics, fronts, and physical processes. He has led large international collaborative projects on the Bay of Bengal and currently leads US efforts on observations of ocean-atmosphere coupled dynamics in the Arabian Sea. Thank you, and I will hand over to Manigandan Mathur.
Thank you, Debashish, for the introduction of all the panel members. So I will get started by giving a brief overview of the center's activities, following which we will have a panel discussion moderated by Professor Eric Dazzaro. Let me share my screen. Tanya, are you able to hear me and see my screen?
Yes, yes, Professor. It's all good.
Okay, so I'll get started. Welcome everyone to this webinar on the Geophysical Flows Lab, a center of excellence recently established at the Indian Institute of Technology, Madras. Shown here in this picture is satellite image of the sea surface temperature distribution, a representative SST distribution over the Indian Ocean region. And I would like you to note the strong horizontal gradients that are present, and also spatial scales that are much smaller than the sizes of these box or grid that you see on the image. Thanks to our collaborators at the Space Application Center of ISRO for providing this image. To summarize the salient features of our Center of Excellence, we are having the goal of establishing an international center of excellence that involve academia both from Indian institutions and international universities, and also closely working with key national labs in India and abroad. And our main approach is to make sure we have a unified approach towards geophysical flows, combining field measurements, the classical oceanography and meteorology measurements in ocean going field campaigns, and interact closely with the national labs and other researchers on large scale climate and weather modeling, and also see how these efforts can be complemented by fundamental studies that we undertake in the lab of specific processes that occur in the ocean and the atmosphere. Applications span a wide range of areas that are all of significant societal significance, including improved modeling and understanding of the climate and the weather, and improved monitoring of the ocean environment and other geophysical systems, aligning with some of the goals of the United Nations. Finally, from the technology viewpoint, we are undertaking in-house development of unmanned aerial systems for oceanography and meteorology to complement existing measurement methods. To summarize the participation from various members of the team, we have around 15 faculty members at IIT Madras, spanning 6 different departments, so indicating it's a strongly multidisciplinary approach that we adopt in this center. We have active collaborations with around 20 different faculty members and researchers internationally, 5 different labs of the Indian Ministry of Earth Sciences, the Space Application Center of the Indian Space Research Organization, and finally close interactions with the Indian Navy, who have been kind enough to facilitate the deployment of our unmanned aerial systems across various field campaigns. The specific faculty members at IIT Madras are listed here. I'm not going to read every one of them for the interest of time. And we also work with several academic collaborators across various universities in India. And as I already mentioned, we think we are uniquely placed in terms of expertise in geophysical flows, fundamental studies of geophysical flows, and also technology development concerning unmanned aerial systems. And we are also uniquely placed in terms of close engagement we have with national labs and academic collaborators in these areas. Okay, this is a summary of our wide reach both within India and internationally. So to get into the science of what we try and study, what are geophysical flows? These are natural flows that occur both in the ocean and atmosphere on Earth. These are inherently multi-scale in nature, in the sense that you can have forcing both in the ocean and the atmosphere spanning a few meters to several hundreds of kilometers, and you also have boundaries that enable processes that can occur over few centimeter scale to several hundred kilometer scales. And these in these multi-scale systems, processes occurring at these different scales interact with one another, thus making them quite complex and also at the same time very interesting to study. What is our focus? We are trying to see how these geophysical flows influence the climate and the other environmental processes that finally influence or affect the society. Shown here on the right top, is a zoomed in image of the sea surface temperature distribution in the Bay of Bengal, which is one of our focus regions of study. And again, as I highlighted in the first slide, we see very strong lateral gradients of the sea surface temperature. And so it's also indicative that there are processes that are occurring even at scales much smaller than 100 kilometers, the so-called submesoscales. And our interest is to see how these processes actually influence the large scale weather and climate in the region. And at the bottom right, we show a sample of how some of these flows can be studied in isolation in laboratory experiments. This is an experiment studying this geophysical flow models in a rotating tank setup. Okay, so with respect to what we focus on, as I said, we are interested in these submesoscales or less than 100-kilometer scales present in the oceanic flows and how they influence air-sea interactions in the region. And which region do we focus on? We are largely focused in the Indian Ocean region. There, India already maintains, with international collaborators, an excellent and intense mooring network array, which all make continuous measurements of the upper ocean and the ocean surface, the atmospheric side, the ocean surface. These are year-long measurements that are being made, as you see in this picture, in the map that is shown here. And what is most evident here is that the coastal regions are under observed for multiple logistical and scientific reasons. And we believe there are processes that occur in the coastal regions that are of that can be of significant impact to what happens in the open ocean and ultimately the air sea interactions that occur in the region. In fact, one of the recent climate model studies indicated on the right here has shown that accurately representing the upper ocean or the sea surface characteristics in the coastal regions of the Bay of Bengal is of huge significance in terms of where the depressions, the predictions from the model on where the depressions originate and how they evolve within a monsoon season. So for these reasons, we are trying to understand what are the coastal zone processes that occur in this region and how they influence the various scales in the sea surface and the upper ocean properties. So the first part, we have been doing this for a little more than 2 years now as a center activity, which is building on more than a decade of collaborations with several of us here who have joined to this webinar and our team. So we've been developing unmanned aerial systems completely from scratch in-house and trying to evaluate how feasible it is for it to play the role of what weather balloons do. Weather balloons are these helium-filled balloons which have a sensor known as the radiosonde, which measures the humidity, wind, and the temperature, vertical profiles of these properties in the atmosphere. These are launched once in a while, scarcely distributed both in terms of in time and space. And we are trying to see how well we will be able to make such controlled measurements on a repeated basis, at least in the lower atmosphere, using drones that move up and down vertically. So shown here is an image that shows the hexa rotor vehicle that we have built here and demonstrated that it is capable of operating successfully in these harsh ocean environments, and we have also been able to make atmospheric measurements. So here shown on the right top as I speak, you see a video of a successful deployment of this hexarotor vehicle aboard the Sagar Kanya research vessel of the Ministry of Earth Sciences. So we have established that it is able to take off and land on a moving ship platform and also make measurements in the atmosphere. Shown here on the bottom is a sample image that we took from a visible range camera that we had included in this drone system. And what we see is an image which is spanning around 1 kilometer by 1 kilometer. And what we are interested in is to look at the fine scales that are present in the sea surface using such images. In fact, shown in this image itself is the presence of a front that you see in terms of the difference in colors on the left and the right side of the panels. And we are interested in seeing what drives these fronts, what are the processes that could occur on these fronts that ultimately affect the air-sea interactions in the region. I would also like to highlight how the execution of such a field campaign is strongly multidisciplinary activity, which involves contributions from many different organizations that are listed here. So in that sense, this executing such field campaigns complementing classical oceanography and meteorology requires a center such as ours to be able to execute on a sustained basis. Of course, the drones are not going to answer all questions we have. They are meant to complement what is already possible. So shown here is an example of classical oceanography measurements we have undertaken in the recent past, where we made measurements using conductivity temperature probes and also vertical microprofilers that measured small scale turbulence in the ocean in the continental shelf region in the North Bay of Bengal. Specifically, we were interested in the internal tide generation in this region from the continental shelves and how they may result in mixing either locally in the generation region or how they may carry large amounts of energy into the deeper oceans before they contribute to vertical mixing in the ocean. We are also working with the National Institute of Ocean Technology on mood buoy data analysis from the buoys that I showed in an earlier image, and working with several of our international collaborators. We are trying to quantify the relative importance of largely 1D processes and inherently three-dimensional processes, the relative importance of these in determining the air-sea interactions and ultimately the climate modeling in this region. We are also interested in addressing some of the related research frontiers on the atmospheric side. Shown here is an example of a large-scale mesoscale system in the atmosphere during the monsoon. This is This is an image taken from a U.S. research vessel in a joint cruise between India and the US. And it is also known that such large scale systems can have smaller scale flows. Thus, which seed new clouds. So, again, like in the ocean, we are interested in the interaction between these large and small scales in the atmosphere, and particularly how they may be interacting with the various scales on the upper ocean side as well. And to summarize some of the questions regarding the atmosphere, can our drones in the really long run replace weather balloons? At this point, we are thinking about how they can complement or at least partially replace weather balloons to make important measurements in the atmosphere. We are also interested in the role of particles that are suspended in the atmospheric boundary layer, both from a fundamental science viewpoint and in terms of sustainable cities, particularly in the coastal regions. So, urban haze is the scientific term referring to all kinds of particles that are suspended in the atmosphere. Again, can our drones be used to measure various atmospheric parameters of importance and contribute to both improvement in the regional climate models and finally addressing questions related to urban sustainability. And to complement these field campaigns, we also undertake fundamental studies in the lab looking at specific processes. As I highlighted earlier, there is a multitude of processes going on in these geophysical flows. Shown here are some of the examples of particular specific processes that we study. Finally, thinking about how better understanding of the physics of these processes could contribute to representing them better in large scale climate models. So on the left is the image showing the effects of density stratification. So the atmosphere is stratified in temperature and the ocean is stratified both in salinity and temperature. This allows for the generation and propagation of what are called internal gravity waves that can carry a large amount of energy, but more importantly, they can carry them far away in spatial extents and contribute to vertical mixing far from where they're actually generated. Shown here in the bottom panel of the left figure is thinking about how small particles such as planktons and marine snow could move in a stratified environment. Shown in the middle panel here are studies that think about how particles influence various processes concerning eddies. Specifically, if you have a large scale eddy but suspended with particles either in the atmosphere or the ocean, can they influence how these eddies evolve? How significantly do these particles influence existing instabilities? And even more interestingly, can there be new instabilities that are caused entirely by the presence of particles in these flows? And finally, we are also looking at some of these small scale interactions that occur on the ocean surface due to wave breaking and the resulting suspension of several ocean droplets, and how they may influence the momentum transfer both from the ocean to the atmosphere and vice versa. And these are processes that I would like to highlight that are underrepresented in climate models whose grid sizes are fairly large compared to the scales at which these processes or flows occur. I would also like to show a small movie on what kind of studies we do in the experimental facilities we have set up. So at the center, we have experimental facilities to study both the effects of stratification and of background rotation. So in this specific movie, we're going to see a specific flow process that occurs because of the background rotation, and the fact that the background rotation, the the extent to which the background rotation plays a role is different at different latitudes. And such systems support the propagation of what are called Rossby waves. In this specific experimental setup, we have a rapidly rotating platform, and you have, instead of the winds or other forcing, we have a rotating annular lid forcing a jet, and we look at how this jet interacts with bottom topography in these experiments. And the main summary in these experiments is that you have at initial times a series of small scale vortices that are initiated by initial shear instabilities, and as the flow evolves, these small scale vortices combine or merge to form larger scale vortices, much like what we observe in the ocean, in the upper ocean. And finally, we are also able to show that these interesting mode shapes established by the Rossby waves also seem to act like barriers to transport. This is of large significance in the ocean and atmosphere, where we are interested in how transport of various species like heat or various chemical species or material are influenced by the physical processes of flows that occur in the region. Okay. In addition to the research activities, we are also very keen on regularly conducting training workshops and discussion meetings. These are all international events that have participation both from India and abroad. We also are hosting international and national researchers giving lecture series. Our students and faculty take part in ocean going field campaigns in the US and other places. We also are engaged in experimental research with various labs in Europe, and we also run a seminar series as part of the center. The overriding goal of all these activities is to ensure wide dissemination of state of the art knowledge, and to be helping with capacity building in these areas in India and to a little extent internationally. So with respect to science and technology goals, we are continuing with our field campaigns looking at the coastal regions and the submesoscale flows that occur both in the Bay of Bengal and the Arabian Sea. The process studies or the fundamental studies in the lab right now focus on internal gravity waves, instabilities, and the transport and mixing in these oceanic flows. And we are looking at quantifying from the wide wealth of data that have been collected from the open oceans in the last decade or so, trying to see if we can quantify the relative roles of 1D and 3D processes in the Bay of Bengal and how they may influence the performance of climate models, weather models in these regions. What are the various physical processes influencing the ocean biology is also a question of interest that we are trying to address in the center. With respect to our technology development, working with the Ministry of Earth Sciences labs, can our drone-based measurements be extended to other systems, including mountains, rivers, and glaciers? What are the main challenges involved? Perhaps some of these questions will be taken up during the panel discussion. And finally, we are very thankful for the support from the Ministry of Earth Sciences for our efforts. And some of these points that we are interested in, I've already highlighted. We're also interested to see if the drone technologies that are generally designed and developed for environmental monitoring, can this become a large-scale community effort to collect data intents both in space and time over probably the next decade or so. We would like to become one of the main important the centers of engagement in India for international agencies like the Office of Naval Research, CNRS France, and other related organizations. Regular training workshops and discussion meetings are an important component for wide dissemination of knowledge in the field. Finally, I would finish by saying that IIT Madras has also recently launched a School of Sustainability. Some of our activities align with the goals for this school, and we are also thinking actively towards addressing some of the United Nations sustainability goals. I will stop at this point and leave the floor to Professor Eric Dazzaro to follow this up with a panel discussion. Thank you very much.
You can hear the applause. Okay, so for about the next 15 minutes, we're going to do a panel discussion of the panel members, who I believe you can see on your Zoom. And I have a bunch of questions for the panel to help moderate this. So the first question revolves along what the region and focus of the center is and why that's that. And I'd like the basis. I'm going to start addressing that question, and then we can move on to some others.
Thank you. Mani had mentioned that Dr. Srinivas Kumar of INCOIS might be here. So I think a comment on the possible applications is in order. As we know, deeper knowledge helps guide advanced systems for ocean prediction. It's an important problem in the context of many of the things Mani said. Srinivas is not attending today, but as director of INCOIS Hyderabad, he leads a multidisciplinary team that uses satellite data, sophisticated instruments, and more and more comprehensive computer models to forecast ocean currents, waves, extreme sea level, and potential fishery zones. These are of interest to very large communities in India. Almost everybody in India is interested in one or the other aspects of the activities of INCOIS. I thought I should mention that. Srinivas would have done it if he was here.
So he has a health condition because of which he was unable to join. So
that's right. Yeah, and then we can go on from here. As Mani mentioned, there are so many open problems and so many possible applications. The number of applications and demand for services is growing, both internationally and in India. And I suppose that some of the work that this geophysical fluid labs will do in the next decade or so is going to be an important part of feeding into these applications. Thanks.
Amiten, did you want to add something to that?
Yeah, I wanted to say that GFL is doing, contributing in many ways. One of the things that I was very heartened to see was the cruises in the local waters, particularly the Paradeep cruise that Professor Mani talked about. I think more such studies near the coastal regions in India are of great importance to understand the coastal processes and the processes that lead to modifications of current structures and in these regions. So I'm very glad to see that.
So a second question, which I'll also direct to Amit, is how are the efforts of GFL related to international research on similar topics?
Thank you, Eric. So I would say GFL is just like many other international centers at the cutting edge of some of these processes, both from the point of view of being involved in their own work in terms of the development of UAVs to sort of supplement or replace the atmospheric boundary measurements, onto the kind of lab studies they're doing that are done internationally to understand the geophysical flows, and efforts at the smaller scale. Further, they've been very closely involved, as Professor Mani mentioned, in the observational programs in the Bay of Bengal that have gone on for almost the past decade. US, India, and various other countries have been working closely in this region, collaborating together, working on global Indian research vessels as well as the US research vessels. We've worked together for almost a decade now. We are now also beginning to do measurements on the Arabian Sea, and so there's a major effort between US and India. Again, Professor Debasys mentioned INCOIS, which is involved as an institution. In fact, fairly soon, in about less than 2 months, we are all going to converge at IIT Madras for a workshop and international discussion meeting on topics very much of interest to the GFL and the international community. So just to summarize, I think GFL is making a mark in the international arena by working on such topics and also collaborating with well-known international centers on such topics.
Thank you, Amit. I'd like to direct the next question to Emily Schroyer. Question is, how are these efforts relevant in international context, in particular with respect to the efforts of the Office of Naval Research in the US?
Sure. So I'll mention a few things that come to mind. The first has been hinted at already. I'm representing ONR's contribution to this Indian-US collaboration known as a CAMSAT in the Arabian Sea. And it's essentially aimed at understanding why all coupled climate models, regardless of what agency or nation is running them, have biases in the sea surface temperature in the Arabian Sea and the moisture in forecast of the monsoon. And so the center's work on both observing and also understanding of air-sea interaction processes at small scales, the submesoscales, is directly relevant to that effort. These are scales which tend to not be resolved in our forecast models. They have to be parameterized, and so we really need to have that basic physical understanding of them. The other aspect that comes to mind are the development pieces with the drone, the UAV. Those systems are kind of unique. It's one of the few systems that can coincidentally sample the upper atmosphere the upper ocean and lower atmosphere. They provide very novel measurements in terms of understanding of air-sea interaction at these high resolutions. And so I think the development efforts that the center is leading there has large international interest as well. I'll add, in addition to the role of UAVs and understanding of air-sea interaction, is also coastal processes. I think they're seeing high use there. And in particular, as we think about climate risk and sea level rise and understanding, local implications for that risk, which depend on the evolving bathymetry near the shore and coastlines that humans interact with and can influence, mapping by drones and understanding the circulation in those near shore regions is very relevant. And then the last piece that comes to mind is the work on the internal tides. That currently is a study of a multi-institution agency support in the US. There's a large, what we call the National Ocean Partnership Program on internal waves, and trying to understand their impact in the coastal ocean, which can be a challenge. And so the center's work there is directly relevant to some of that international work that's being supported in the US right now. I guess I'll stop there.
Okay, another question is respect to the technology of the drones that have been developed. And the question is, what are the main technical challenges in developing these drones in the context of the GFL Center? Why not just use off-the-shelf products? Why are they being developed here? And I'm directing that question to Bharath.
Okay, thank you very much, Professor Eric. Yeah, so it's a great question because there are so many drones that are out there. So why not just use one of them? And as has already been mentioned, the number of applications are innumerable. So what the GFL actually does in a way is give us a focus and allow us to actually build vehicles that would work for this type of an environment, which has already been mentioned, is fairly harsh. We're trying to go in the middle of the sea and fly up to a couple of kilometers vertical profiling. So when you look at what's there off the shelf, none of them are actually able to handle these conditions. And you either find really small ones that are not suitable for this purpose, or really big ones which are, again, not suitable for this purpose. So there is this sort of niche gap in technology where the JFL is actually able to help us develop these vehicles. And there are a lot of experts on aerospace systems and technologies in this JFL, so that really helps and contributes. The other part is payloads. Right? Payload development is something that is also quite critical. And because we're not really sure what to expect and what are the type of sensors we need, we always don't need the most high-end product off the shelf. Simple sensors, simple wind sensors, cameras, etc., actually can give you phenomenal wealth of information. And the fact that the center puts together its own vehicle sort of allows us to integrate these, play with it, and it's sort of a mix and match that really helps us. And I think with all these points, it sort of is quite unique in that the GFL, through its problem statement, actually helps develop these technologies, which can be used for many other purposes, I'm sure. But presently, we're just focusing on, say, upper ocean and lower atmosphere.
Yeah, good. I have a follow-up on that, and that is, could you give an example or two about the various sensors that you're trying to develop, and what type of products would come from those?
Sure. So if you look at right, so there are images here on the screen, and the type of information that we want are, say, wind, temperature, pressure, relative humidity, and some, let's say, sea surface images, maybe the visible, maybe the infrared, etc. So to begin with, since there are only so many things we can start developing, there is, some of these are either off the shelf, high end, or more often than not, simpler ones. So an example is, let's say, if you look at our camera phones today, they're not each sensor is, they're not very high end. There are a bunch of small, low end sensors that sort of put together and give you a composite image. To specifically answer your question, what type of sensors are we looking to develop? We're looking to develop. There's a new field on photonics, which one of the members of the GFL is working on, and these are really tiny sensors that can be integrated onto unmanned aerial vehicles. And the interest is to develop in-house photonics-based sensors to pick up, let's say, vehicle acceleration and position. Right? And these things can translate once we sort of mature the technology, things can of course translate to other vehicles and other platforms. That would be an example.
Good.
Eric, can I
Please.
a little bit? I have a question for Bharat. Bharat, there is also some interest in the sensor group, from the sensor group at SAC. They see promise in the drones that you're developing, and there's going to be a discussion, I hope very soon, with the SAC sensor development group. they are very interested in exploring what sort of sophisticated or intermediate sensors your drones can carry. Is that right?
Yeah. Right. So that is, I mean, we'd of course be, quite happy to collaborate with them and find out what payloads we can put on our vehicle. And I think that sort of is ties towards what these vehicles can do. And over here on the last point is extended range, endurance, altitude. So if you want to make these sort of measurements for meteorological purposes, then we need to be able to fly for a large number of hours, and that is not capable with a basic battery technology, and you can't do that with a vehicle that weighs 5 kilograms or 6 kilograms. So we need something that can carry of the order of 10 to 15 kilograms for a couple of hours,
Right.
up to an altitude of 3 to 4, say 5 kilometers. Right, so that's a big ask. Carry 10 kgs for say a couple of hours at 5 kilometers is a difficult task, but that's really what the technology that we're developing is going towards. And so, yeah, absolutely, we'd be more than thrilled to, uh, have these conversations and figure out how we can pitch in and push the barrier forward.
Yeah, can I just add something, Eric?
Please.
Yeah, so this interaction with Space Application Center is very complementary in the sense that they see a huge potential for our drones to act as testing platforms for many payloads like microwave, synthetic aperture radars, mini synthetic aperture radar, those kind of payloads that they develop in-house. They see these as potential testing platforms. They also look at these as opportunities where they can test some of their retrieval algorithms that they use on their satellite data. They see benefit in doing testing some of those algorithms on our drone systems by having their payloads on our drone systems, and we see the interaction with SAC as beneficial in terms of bringing in sophisticated payloads to be mounted on our platforms for these applications, and also they bring in a wealth of experience on how to analyze the data that you collect from some of these payloads. So yes, a formal discussion is going to happen soon between the center and the Space Application Center on some of these aspects. Thank you.
Okay, so moving along, another question is, why are the lab scale fundamental studies relevant to what we've been talking about? And I'll direct this to Anubhav. And
Yeah, so a lot of these lab scale studies that we are trying out, especially trying to map these fundamental problems, they are done in a very approximate manner in terms of how they enter into the large scale modeling. Especially if I'm just focusing on, I'll just for the time constraint focus on, let's say, the particle transport in the ocean. This is an increasing problem of interest, whether we are thinking of in terms of microplastic transport or rather be the biogenic mixing by marine organisms or marine snow. There is a lot that we don't know in terms of simple questions like how much fluid actually is being transported. And when we think of this in terms of the volume of particulate matter that is there, the uncertainty plays a big role when we are trying to quantify this in larger models. So that's primarily how we are thinking about it, that if we get more precise answer regarding these transport processes through the lab scale fundamental studies, they can at least be a beginning process of being inputs for the larger models.
any further comments on this from the panel?
Yeah, in addition, we also trying to work on understanding the physics of internal gravity waves and vortex instabilities. With respect to internal gravity waves, we are studying both what are the mechanisms by which they get generated. For example, when barotropic tides act over topography along the continental shelf regions, and we're trying to see if we can extend some of those studies to estimating how much energy may be put into internal tides in this, let's say, around the Indian coastline. And with respect to instabilities, we're looking at the physics of, let's say, the roles of various parameters in the problem. on instabilities that occur in the large-scale vortices that are observed in the upper ocean. And the idea here is that if we understand the mechanisms by which these vortices go unstable, finally we could start to think about how they may be contributing to mixing that occurs in the upper ocean and ultimately to the air-sea interactions in the region.
Okay, so for a final question, Direct Tamani, is what's the relevance of this center to UN sustainability goals?
Yeah, so we are looking at a couple, 2 or 3 different sustainability goals, one specifically on water. So we think we can contribute to an improved monitoring of the coastal environment, both in terms of the ocean biology or like Emily pointed out, looking at the coastline or the sea surface height along the coast. These are important both from a fundamental science viewpoint, which we have been highlighting a lot, but also in terms of making sure we preserve the coastal environment and plan development in these coastal regions better. In fact, one of the slides highlighted how the design or planning of these mega cities in the coastal regions have to carefully incorporate the corresponding climate impacts. So in that sense, we are contributing to some of these UN sustainability goals.
Okay, thank you. Thank you. That finishes the panel discussion, but we have lots of very nice questions. Thank you to the audience for contributing these. That if you should put them in the question and answer box, not the chat box, because that's how I get to see them. There were a number of questions. I'm going to direct this to the basis about the relationship between GFL and the numerical prediction models, which are the basis of an awful lot of our understanding and applications of the climate system. And so the question was, how will GFL contribute toward improving them? Are we working with existing models or new models? That class of questions.
All right, I will try to answer that question. It's a very good question, but a very large one. Let me take just 2 examples. There is a river that originates just north of Bangalore in Nandi Hills and flows about 500 kilometers just south of Chennai near Mahabalipuram. That river often runs dry, and that river does not appear in our climate models. Yet millions of people live on either side of that river. Surely there is need for better understanding of these minor rivers in peninsular India. Can we answer simple questions like, how likely is it that in the next decade or 2, it will run dry for 2 or 3 years in a row? We don't know the answers. In a small way, the Geophysical Fluids Lab, particularly the drones, might make a contribution to this, but through simply monitoring stretches of that river, the estuary, where is it dry, where is it not dry? I'm not saying that 1 or 2 drones can do this, but in a few years' time, maybe you have set an example for others to do this monitoring. State agencies, for example, are good at doing this sort of thing. The second very broad answer of the importance of numerical models is the present day climate models, however fine resolution they are, they go up to maybe 12-kilometer resolution in the horizontal. Most of them just drizzle, they do not give intense rainfall. And that's been a long-standing problem with these models. And as you know, drizzle is not going to represent monsoon rainfall very well, or river hydrology. So there are contributions to be made from GFL, from the fundamental studies that all of you are doing, to eventually getting these models to do a little better on monsoon rain.
So to give on the last point, just to give a specific example that came from previous collaborations before GFL was founded, one of the big realizations was that the models have biases in how they represent the upper ocean. They make the mixed layer at the upper part of the ocean too thick. They all do, mostly because they didn't even know that it was as thin as it really was. Sometimes it's a few meters thick, and they were making it 10, 20 meters thick because they only had grid points in five. They couldn't even resolve a 5 meter layer. And it was eventually shown that has a big impact in weather models on the amount of rain in India, and thus whether or not that river goes dry. So that's an example where there was a fundamental knowledge which directly will help, we believe, predictive models.
Absolutely.
Sorry, someone said something. No, there's a number of questions about technological challenges and limitations for UAVs. And so if we could get back to that topic, what are the technical challenges for improving the UAVs and for the new ones that are being developed?
Professor Bharat?
Yes, sure, I can go for it. I think the challenges revolve around what is being asked. And what is being asked is you need to fly really high, you need to fly really far, you need to fly longer and efficient. So we want the best of everything. And it's only then that we'll be able to come close to answering some of these questions. So each one of those puts a significant amount of strain on the technology and the technical development. So to give you, take one example, a lot of the unmanned aerial vehicles we see are battery powered because they are low cost. You can actually get them. There's a reasonable TRL with it, and you respond quickly. But there is an inherent limitation with these sort of battery-based electrical propulsion. And one of the things that, let's say, the center is looking to is to switch away from to switch away from batteries and start using internal combustion engines. But that comes with a whole host of problems. The reason we'd like to use that is because the specific energy of fuel is much higher. So if you take away a battery and you put an engine plus fuel of the same, say, weight, then your endurance immediately shoots up. But that has a lot of challenges that come with it. For instance, one is if you have an engine, it's going to create a significant amount of vibrations associated with it. How do you isolate that? Then you have to make sure that fuel is always flowing in it. So sometimes you might want your vehicle to fly around quickly. So there are issues with fuel starvation and a whole host of problems. So I'm just picking one subsystem here, but you can actually go through each subsystem, and there is a need to actually develop. And like I said, there is a band here, which is not the really small vehicles, it's not the really big vehicles. So we have to be really frugal in terms of the technology, try to make it as efficient as possible, but at the same time, try to keep it as light and be sensitive to the weight that we're adding. Because at the end of all this, it's only useful if you can carry the payloads we need to actually make the science measurements. So as far as, say, the center is concerned, the UAV is a sort of a tool, right? It is a instrument that will give you the data, which will go which will take forward to answer some of these scientific questions. But the challenges on the technical side are to do these things, not to mention that we are supposed to fly in really gusty environments. Right? So imagine you have a vehicle and then a huge amount of gust comes through. You should be able to, pick up that gust, because that is what is really important. It's if you're flying in really calm environment, then there is nothing to pick up. There is no wind, so there's nothing actually, no data to feed. So you do expect a fair amount of, I'm going to say, unpredictableness, because we're not really sure what's going on there, at least at the fine scales. So it is a technical challenge to be able to build vehicles that are robust and can handle these sort of conditions. One thing that we are not looking at right now, but maybe something to look into the future, is can you actually fly these in rainy conditions? Right now, we're sort of staying away from it. We're not touching rain. We're not touching any precipitation. But I'm sure there's a lot of questions to be answered, a lot of data to be collected when the weather is not, quote unquote, ideal for flying. I think so. That sort of gives a flavor of some of the challenges technically for.
And there was a related question, which perhaps you could briefly answer, which is how much you're thinking about artificial intelligence and things like that to help control the drones in these complicated situations.
Right. So, artificial intelligence is definitely something that we incorporate at different levels. I mean, the idea behind artificial intelligence is first you need to build and train it with some data that we are confident in, and then it starts sort of developing on its own. Uh, so, definitely at this stage, at least let's say to take the to say sift through the images, maybe not much, but that is one of the goals as we move along and as the technology matures, as we start doing more and more of these field campaigns, we're going to start getting much more data, and it's going to tie in with what sort of questions we are trying to answer at that point and how best we can use AI. But it's definitely something that's come up many times, how best to incorporate these AI ML neural networks sort of technologies.
So we're getting close to the end of our time. There are two questions here which I thought would be a nice way to sum up. There's a question about why is the ocean so poorly understood, and a related question about how do we see internal gravity waves? And I think these are sort of related. If you recall in the presentation, there was a picture of SST, of sea surface temperature from satellites, and what you saw was a lot of very fine scale behavior. That the satellites could barely see it. They have a resolution of a kilometer. That part of the ocean is 1,000 kilometers across. So the short answer is why is the ocean poorly covered? Because it's really complicated. Because it has a lot. It's actually considerably more complicated, perhaps, than some of the other. I don't want to say that. Never mind that. Anyway, it's a complicated thing. And so we need to look on a very large number of scales, and GFL is focusing more on the smaller scales because that's where we know the least. And to be specific, the question was, well, how would you see gravity waves remotely? Right? One of the things that gravity waves do is they change the roughness of the sea surface, and you can see that through sun glitter. You can see it through SAR, radar backscatter, which is similar to sun glitter. You can also see it in the altitude of the surface. So those are somewhat indirect ways of measuring something which traditionally would have to be measured with a ship. And this is one of the things that's being aimed for. So maybe does anybody in the panel who's been looking over the questions want to emphasize any of the other questions that I missed?
I think there were a couple of questions related to tsunamis and earthquakes generated in the ocean. I would just like to point them towards the Indian National Center for Ocean Information Services, who already have an excellent tsunami monitoring system. They have measurement systems in the ocean that can give sufficient warning if tsunami is generated or we are in potential danger. So we are not working directly towards any of those questions, but INCOIS is an excellent place, which is not just developing some of these systems, it's deployed and it's in operation. So I just wanted to direct them towards INCOIS's efforts on this. And yeah.
So I thought we'd finish off here by going back to Mani, who may have some closing remarks.
Yeah, thank you, Eric. I would once again like to thank all the panel members, my colleagues from GFL, and all the audience who have enthusiastically participated in this center. We see this as an activity for the next several years, trying to contribute in our own small way towards these complex problems that are of relevance to the society, both in the Indian subcontinent and the international community. So a lot of information about our center's activities are up on the two websites that are listed here. The first one contains these basic science information, and the more recent events and the upcoming events could be found on the second web link that you find here. We are continuously running these seminar series and workshops. A lot of this discussions and material go up on our website, so please do look for updates on this website if you are interested in these topics. Again, thanks a lot to everyone for participating in this webinar at a not so goodly hour either for people in India or our international collaborators who have participating from the US. It's quite early in the morning for them. Thanks a lot, everyone.
Thank you. Thank you, Professor Mani, for that great session and your team, all the panel members. It is really great. And thank you, audience, for staying with us, joining us tonight. So we had a bunch of questions on the certificates. Everyone, please write or follow those links that I've just posted in the chat box. We'll post updates. So this is a series of 15 webinars, and this is the 4th webinar that we are on currently. We have another session tomorrow, so please do join us for that. And yeah, like I said, please follow our social media links that I've posted in the chat box, right? So thank you everyone. See you.
Yeah. Thank you, Eric. Once again, thanks, Dania, for your help.